Well, maybe we'll start. Good morning, good evening to everyone participating, and thank you. It's a real pleasure this morning to introduce Kevin England. And many of you know Kevin, and Kevin is currently the sole proprietor of EK Petro Consulting, LLC. And his BS degree is in petroleum engineering from the University of Tulsa, and he also has an MS degree in petroleum engineering reservoir management from École Nationale Supérieure du Pétrole et des Moteurs in France. And Kevin has more than 40 years of experience in the oil and gas industry. 34 of those were spent with Schlumberger. And that started with Dowell Schlumberger. And in that capacity, he gained extensive lab, field, technical, and management experience. And so he has worked on projects with a wide range of challenges worldwide. And this has been in more than 50 countries. And this was until his retirement from Schlumberger in 2018. And he is currently a consultant for the energy industry and has worked on projects for well construction, stimulation and production optimization, carbon capture and storage, as well as geothermal. And Kevin is currently consulting to the University of Utah on the Utah Forge project. And without further ado, let me introduce Kevin England.
Thank you very much, John. So John, was a mentor of mine and one of the first persons that I met when I started with Dowell in 1984. So I've known John for a very long time. So it's a pleasure to present what's going on currently at Forge. Today's focus is on the 2024 stimulation program that was done in April of this year. Just to remind that Forge is basically an underground laboratory to develop, test, and prove different concepts and materials and tools and technologies for application in enhanced geothermal systems. So just as a quick background to get to where the phase of fracturing happened in this year. Initially, there was a lot of work done at Forge to drill monitoring wells and understand the geology much better. The first thing that was done for the doublet that becomes the injection and production well was to drill injection well 16A 78-32, which I'll just refer to as 16A. It's shown here in the red line down here. It was drilled at 65 degrees from vertical down to a depth of about 10,947 feet. In April of 2022, there were 3 frac stages pumped at the toe section of the 16A well. And I'll talk more about those in next slides. The purpose of that mainly was to understand the fracture propagation and geometry in order to place the 16B 7832 production well, to drill that well to intersect the microseismic cloud from the fractures that were generated from 16A. And then in April of 2024, this year, there was 9 stages of fracturing performed in 16A and 4 stages of fracturing performed in 16B to provide the connections to evaluate the circulation potential between the injection and production wells. So this is just an overview of what Forge looks like, the site. The 16A and 16B wells are both drilled from a single pad up here in the upper left. This is the projection of the 16A well out into space. And then you can see the offset wells, which are three used for microseismic monitoring here, triangulated around the lateral so that we get good microseismic resolution on the hydraulic fractures that are created. EGS is hot, so all of these wells, when you plot them all on each other, true vertical depth, we're in the where we're stimulating, we're definitely in the 390 degree to 430 degree Fahrenheit window. So just going to review real quick the stages that were pumped in 2022, just for reference, because when those were pumped, the idea was to try and understand everything about the fracture initiation, the fracture propagation, and just the general behavior of the fracture in the granitic formation. So the first stage was actually pumped in open hole. But in the 16A well, there's a 7-inch casing set, and then there was 200 feet of open hole below the casing shoe. So the first stage was pumped in the open hole, and we just stepped up the rate up to a maximum rate of 50 barrels a minute, and at the end we stepped down, and that was all in an attempt to gather good data points on fracture behavior and then get some idea on friction behavior at the end of the treatment. When these stages were done, the wells were shut in and then were flowed back for a period of time to reduce the wellhead pressure, because the isolation mechanism for the stages in 2022 were retrievable bridge plugs that were run and set on pipe. Stage 2 was pumped through a perforated interval in the 7-inch casing. So the rate was 35 barrels a minute max. You can see at the different steps the pressure behaviors. And then we did 2 planned shutdowns, one initially when we got to the initial rate of 5 barrels a minute, and one when we were at the maximum rate of 35 barrels a minute, again, in order to understand the fracture behavior and get some good data on the net pressure that was being developed in the fracture system. Pressure was monitored again, and the well was flowed back so the next bridge plug could be set. And the first, I should mention, the first 2 stages were pumped with slick water. And stage 3, we actually pumped cross-link CMHPG fluid. And we did pump some deep prop. And this is in order to try and get an idea if there were any potential entry issues into the fracture by putting solids into the fluid. So in 2022, there was no proppant pumped in any of these frac stages other than the deep prop that was pumped in stage 3. And the reason for that is the mission was to get an idea on the fracture geometry behavior and all the fracture properties, and not to risk screen out during these stages, so that all the data that was intended to be collected could be collected. So the result was here in microseismic. So this is, the blue is the 16A well. The red is the projection of where the 16B well would be drilled. It's not drilled at this point, but you can see stage 1, stage 2, and stage 3 fracture behaviors. And then based on those location of events, the 16B well, the plan for 16B well was to drill this trajectory that would intersect those microseismic events. So in fact, and that was done last year, 16B was drilled, and it is in the deviated section, in the 65-degree lateral section, it is parallel to the 16A well, and is positioned 300 feet vertically above the 16A well. Monitoring wells are the same for the treatments that were done in April of this year. One thing different on 16B is that there was fiber optic cables run along the outside of the casing and cemented on the 7-inch casing of the 16B well. There are 2 fiber optic cables that terminate down near the casing shoe. One is basically Shell and UT Austin fiber, part of the R&D initiative. And the second one is Silixa and Rice University. And the third fiber optic line was for a ported pressure temperature gauge into the 7-inch casing with a Baker gauge carrier and apparatus. I said, for research purposes, there are a lot of things that get implemented into any of the programs that get done at Forge. One that I won't talk about but is highlighted here is there was a test bridge plug run in the 16B well during stimulation, developed by Petroquip as part of an R&D project done for Forge. So this is a projection of how the wells are laid out in a vertical section compared to each other. The lateral, you can see the 16A well on the bottom, the 16B well on the top, and the height difference between the well bores, approximately 300 feet. Now, one of the primary missions at Forge is observing and understanding induced seismicity with all the operations that occur at Forge. So primarily for the hydraulic fracturing treatments and the flow back and any circulation that's done, there's a traffic light system that's in place. Basically, the observations that are made, the data that is analyzed, the events that are identified, and the magnitudes all have to meet criteria for the traffic light system. And there are a green, an orange, and a red level by which different actions accordingly have to be taken. The bottom line for the stimulation that was done this year is that we did not exceed any of the alarms and stayed in the green the entire time. So let's move to the stimulation that was done this year on the 16A well first. So the 16A well, the injection well, was done first. And remember, the 16B well has fiber optic on the outside of the casing, and then we have the 3 offset monitoring wells for microseismic and plus other different monitoring stations around the sites out there to record all the events that happen during stimulation. The basic plan for Forge is not to do cookbook or repetitive stage type designs. It's each stage is designed with some variable in mind in order to try and understand how that impacts the ultimate fracture initiation, propagation, and eventually connection behavior between the 2 wells. So stage 3R here is actually the first stage that was pumped, and it is a refrac of the 3 stages that were done in 2022. And this time added proppant to that job. So we refract the 3 stages from 2022 and added proppant. The proppant in all cases here was start out with 100 mesh and then finish up with 4070 mesh sand. It was all silica sand used in these treatments. The variables that you can see in this table that we're using to do evaluation is 1, the fluid system. We pump some slick water, we pump some cross-link CMHBG. We look at the effective viscosity on all the fracture behavior. The number of clusters ranges from single clusters to 4 clusters to the last 2 stages having 8 clusters. And then the enhanced proppant transport and placement, stage 6, was designed actually by adding some ultra lightweight proppant material, 3080 mesh omniprop, to try and facilitate better proppant transport, better proppant placement, and overall better fracture conductivity connection between the injection and production wells. So just in a sense of from the design there, you can see that these are the 3 stages from 2022, stage 1, 2, and 3 that were lumped together as 3R for refrac. And then the plan is stage 4, 5, 6 being single clusters, stage 7, 4 clusters, and stages 8 and 9 being 8 clusters. And just one point to mention here, so these wells are deviated at 65 degrees. And so from a fracturing standpoint, I know everybody knows the challenges that can impose on fracture initiation, fracture behavior when trying to initiate from deviated wellbores. This is just an artist kind of cartoon saying that if we generate vertical planar fractures, then these will connect from the injection well to the production well. And this gets a little bit hard to look at sometimes with everything being tilted. So tried to make it a little bit simpler and say this is the same picture, but now I've just laid it out horizontally or flat and showing the different stage locations here in depth. And then what these depths up here represent is if the fracture initiates and connects with a planar vertical fracture between wellbores. Just for reference, this would be the depth directly vertically above the injection well in the production well, in the B well. So just to kind of show what things would look like if everything were perfect. Now, from another evaluation standpoint, we pumped actually 3 different tracers, 3 different types of tracers in the program. One was provided by the University of Utah, the Energy and Geosciences Institute, which were water-soluble tracers. And then the other 2 were, one was supplied by Quantum Pro, and these are the nanoparticle tracers, and then Resman with water-soluble tracers. And a unique tracer was pumped in every stage of fracturing by both Quantum Pro and Resman. And we also, we'll talk a little bit about a circulation test that was done post-stimulation, and all of those circulation steps also had unique tracers placed in them. Now, I mentioned the ultra lightweight proppant. This is just details on the specs of the proppant. It's very ultra low density. So the idea here was to put this ultra prop or omniprop in with the proppant that was being pumped in stage 6, and then hoping that it would facilitate some better transport and also kind of hinder and provide less settling in the fracture to provide better overall proppant placement between the injection well and the production well. Okay, the crosslink fracturing fluid, crosslink CMHPG. This is just an overlay of the fluid stability, the fluid viscosity at different temperatures. So you can see from 200 degrees to 250 to 300 to 325 and 350. The fluid is not stable at the temperatures that we have at forge bottom hole, but we have a lot of cool down in these stages. And so depending on the stage that it gets pumped on, we don't know how far out in the fracture the system will go before it experiences the temperatures that will cause it to degrade very rapidly. But mainly this was an attempt to look at the impact on fracture initiation and probably a bit on the connection and the ability to get proppant entry into the fracture connected to the wellbore based on the fact that the wellbore is deviated at 65 degrees. So I'm going to go through the individual stages on 16A here. And 16A was done by pump down plug and gun method. So following the similar procedures that are done every day in unconventional oil and gas, pump the plug and guns down, followed by pumping the subsequent stage and repeating that process until all the stages are completed. So stage 3R, again, the refrac of the stages that were completed in April of 2022. You can see the rates and the pressures, and the orange is the proppant concentration at the blender, and the brown color is the proppant concentration at the perforated interval. So just the offset in the volume between the surface and the perforations. And this stage treated, very, very well. Towards the end, it got a little bit tight, but we have the maximum allowable surface treating pressure is 8,000 psi. So, we were able to get all the proppant pumped, cut the proppant, and easily flushed underneath the maximum allowable pressure. So stage 4, single cluster. This was again a slick water. This is kind of a similar designed, similar treatment to what was pumped in stage 2 in 2022, except this time we're pumping proppant. So you can see that one thing here I'll mention on all the plots that you'll see is initially when we're starting out the stage, we're pumping at this low rate, and this is because the ball for the frac plug wasn't run with the plug. We dropped it from surface after the plug was set. And so this is basically pumping the ball the rest of the way down and getting it seated onto the frac plug, and then breaking down the formation and starting the actual frac stage. The reason that was done was just as a safety mitigation in case there was no way to break down the formation, or we had trouble with the guns and we needed to run more guns. We wanted to make sure we still had a way to pump into the well before the ball got landed on top of the plug. So this stage, again, slick water, pumping along as planned, and placing the amount of proppant that was intended. So stage 5, very similar to stage 4, single cluster, this time with crosslink CMHPP. Little bit different behavior in some regards. I mean, it's takes some time to get the rate up to design rate just because of the max pressure limitation, but staying with a good safety margin, we get up to rate before proppant started. And this one treated normally, except for there's always going to be some issues in some of these plots that are under future evaluation or under evaluation, I should say, to figure out what kind of artifact this was. Was it surface artifact? Was it a downhole artifact? And all of those evaluations are still currently in progress. But the stage went according to plan, and all the proppant was pumped. So then stage 6 comes along. This is a single cluster. This is where was basically very similar to stage 4 with slick water, single cluster. This is where we intended to pump the ultra lightweight proppant, the Omni prop. So you can see here is that initially when we're trying to get start the treatment, basically we're just kind of pressure testing the casing to some degree, and finally we get a little bit of a break here and start to initiate. Start to get some rate. Remember that even though we're pumping in at very low rates into the formation, there's no matrix flow in this granite. So anytime we're pumping into the formation, we're fracking the formation. But here, albeit at very, very low pump rate. We continued to do that and worked until we got the rate up finally to about 11.5 barrels a minute. But we actually increased the maximum pressure allowable to 8,500 for this treatment. But at the end, after pumping for about 3.5 hours, there wasn't really any way to start pumping proppant at this point. And so decided to shut down. In the meantime, we had been looking at some of the logs, some of the geology features. What we decided to do was go down and add another cluster. So also mention that in 2022, the perforations were designed to be placed where formation image logs indicated the highest presence of natural fractures or drilling induced fractures or even thermally induced fractures, but selected to be at a place where it looked like there was some fracturing occurring at the wellbore. In 2024, all of these perforation clusters are just geometrically placed. So they're based on a set spacing, and there's no consideration for whether or not that cluster sits in proximity to natural fractures. So in looking at the logs, we found that the cluster from the previous attempt, there was no indication of natural fractures. So we added a cluster to this stage where there was presence of natural fractures. And when we started pumping again, bottom line is we really kind of didn't get much of a different result. A little bit more rate if 11 to 16 barrels a minute is more rate, but again, pressure wise, we're just not able to start pumping any proppant without for sure probably screening out. So at this point, we decided to just move on to stage 7, and stage 7 was designed to be 4 clusters. We actually changed it to 3 clusters because of the extra gun that was used for stage 6. And so here you kind of see a haunting repeat kind of trying to build rate, but being at maximum pumping pressure the entire time. So this is kind of concerning because now we're really not able to get good fracture propagation or pumping conditions. So this time, we pumped for over 8 hours in this case, trying to finally, see if something would finally break and we would get fracture propagation. But it never did happen. So we decided to shut down. And of course, in the meantime here, we were looking now at maybe this is a geologic issue and maybe, something that should have been noticed or could have been noticed. And so contacting back to the university and to the GNG folks, this is kind of ironic in a way because this is a spectral gamma ray log, and the 16A well was the only well at Forge that ran a spectral gamma ray. And so just taking the perforation overall depths where stages 6 and 7 were, and looking here just on at the spectral gamma ray, you see there is a definite difference and alterate or different response to the potassium, thorium, uranium, and even the overall obviously gamma ray itself um, that shows up right where those perforated intervals were actually at. There wasn't anything obvious on the sonic logs to show that there was something different in this zone compared to the surrounding zone. So this is just a clue and something that popped out, but is under obviously further investigation and trying to revise possibly the geomechanics evaluations for the future stimulations at Forge, because we definitely want to understand and avoid these kinds of situations. So we moved on to stage 8, and stage 8 was now 8 clusters. And I guess, pointing out stage 8 would have actually been back into this area here where we were outside of this anomaly from the spectral gamma ray log. So crosslink CMHPG, 80 barrels a minute. This job was just, really uneventful. 8 hours of pumping. Had one incident where sand delivery became an issue, but we just modified and then got everything back on track and ended up pumping over 1 million pounds of proppant on this single stage through these 8 clusters. So kind of back on track, set the plug, go to stage 9. Stage 9, the only difference between stage 9 and stage 8 is the fluid. The crosslink, we're back to slick water. Again, here, everything is treating fine. When we get into the one pound stage, partway through, pressure started to increase, a little bit of a break, but then pressure started to increase to the point where we ended up having to cut proppant a bit short. So we didn't get to the 1.25 or 1.5 pound proppant stages in this case, but we still pump over 700,000 pounds of proppant. But this is maybe a key indicator of the fact that the viscosity at the wellbore could be making a difference in the entry of the proppant into the fracture system. So stage 10 was added to the program because of the fact that stage 6 couldn't be pumped, and that's where we wanted to pump the omniprop. So we added stage 10, a single cluster, slick water, same design as stage 6, and ended up pumping the job to completion, and the omniprop was added at a consistent concentration all throughout the proppant stage, the 100 mesh and 4070 mesh proppant stages. So a total of 4,000 pounds of 3080 mesh ultra lightweight proppant was pumped. So this is just a summary of what happened actually, so that this can be compared to the design schedule. And then this is just making the same map, but including changing the number of clusters on stage 7, adding the cluster on extra cluster on stage 6, and adding stage 10 to the figure. So all during this time, we're monitoring all of the frac hits that are occurring at the 16B well during all the stages of fracturing during 16A. Important, this was done on the fly real time because the intervals where we wanted to perforate 16B had to be identified beforehand, because the guns for this well were run TCP, and the guns were being loaded in Bakersfield. And so we had to get the information on where the perforated intervals would be so that the guns could be loaded and the spacer tubes could be installed and the gun systems brought to forge in order to run for each of the stages that were subsequently pumped on the 16B well. So unfortunately, with the time, we won't go into a lot of detail on the fiber optic, but it was instrumental and provided really valuable information all through the program that was done in April. And so this gets done a lot in unconventional oil and gas and in other places, and this is courtesy of Nubrix, who were doing the interrogation and interpretation of the strain. And at the end, just putting a simple plot up here for these interpreted frac hits, locations on the 16B wellbore. We ended up picking about 28 of the best identified fracture hits. We only had 20 guns available, so we went through a process to determine which of these would be selected for being actually perforated and stimulated in 16B, and that was based on one thing was this kind of look. So this is like the map that showed that if you had just vertical fractures connecting 16A, which is the red line, to 16B, which is the blue line. So again, a very deep topic here and a lot of information available and a lot of work being done. But basically, what you can see is that the stage 3R, 4, and 5 from 16A wellbore kind of connected through a similar corridor to 16B. The stages 6, which said we didn't pump proppant, but we did obviously frac and see frac hits at the 16B well. You can see kind of they're not vertical; they're veered off into this direction. And then stage 7, which was at maximum pressure and not able to add proppant, actually veered off more, or it's more vertical actually between the 16A and 16B well. So, you know, this area in here does look like something anomalous in terms of fractures being able to connect something different in this area, which was identified or potentially identified with a spectral gamma ray. So going to stage 8, things got really interesting. The frac was very well executed and nothing really stood out that much. But when you look at the fracture hits on 16B, actually some of the first fracture hits started out further up the wellbore than would have been anticipated. But they started up here and then kind of worked their way back down to being more vertically connected. And so this is a very wide corridor of interaction with 16B from these 8 clusters in 16A. And then when stage 9 was pumped, again, this could be, you know, an artifact of stress shadowing, and the fact that I'm sorry, these clusters moved a little bit further uphole even, and then stage 10 being a single cluster looked like it almost followed the same corridor as stage 9. So really, really interesting results. But based on this, we determined that we would have to divide into 5 frac stages for 16B in order to try and accommodate where the fracture hits actually were, and to try and use these fracture stages to enhance and improve the connection between the A and the B well. So this, again, on the cartoon this is what it actually looks like in terms of where stages 1, 2, 3, 4, and 5. These are the proposed and the actual perforated intervals for the stages that were pumped on the 16B well. So let's look at the behavior of the fractures on the 16B well. And again, all of these are going to be slick water treatments. And the first stage was 4 clusters. The intent was to pump all of these jobs at 60 barrels a minute. And you can see in this case, the rate was achieved, the proppant was pumped as planned, and there were no real anomalies, other than the fact that what you'll notice on all the stages, the frac stages in 16B, is this initial early pressure drop that always occurred, and quite a pressure drop. And the idea here is that this may be the point where the initiation of the fracture from the 16B well uh, achieved a really good intersection with the fractures that were in place from the 16A well. Stage 2 was 5 clusters with slick water. Again, there's a lot of things that look different in each of these stages, but for the most part, all of them were pumped as per the schedule. On this one, we actually tried to pump a bit more proppant and see what would happen. And actually, more proppant just looked like it started to reach a case where we were probably going to end up screening out. So we cut proppant and flushed everything. Stage 3 was 3 clusters. Again, this was pretty undramatic stage. Stage 4, really kind of the same thing. So all the stages from the 16B well went according to the design. Unfortunately, for stage 5, it was only perforated because we actually ran out of frac plugs because of some issues with some of the frac plugs that were run with some failures. We actually ran out of frac plugs and didn't have a way to isolate for stage 5, so we actually just perforated stage 5 without fracturing. So that gives a good opportunity to the guns that were used for perforating the B well obviously had to be oriented because of the fiber optic on the outside of the casing. We used the G-force gun system from Halliburton to perforate at basically 10 350 oriented perforation away from the fiber optic lines. So this is just the actual pumped for the 16B well. And microseismically, waiting for the final catalog of events, but basically all of the stages show up pretty well. And when you get this in a way you can rotate it. There were a few events that were above magnitude 1, these black balls. I think the maximum event the whole time was 1.9. But again, none of the traffic light system alerts were exceeded. And so induced seismicity wise, everything was very successful during the stimulation. So I wanted to save a little bit of time at the end. That's the fracturing summary for the different stages for the different wells. But a couple of months ago, we went back out to Forge and did a circulation test between the wells after the fracture stimulation was done. And of course, after all the plugs were drilled out. And this is kind of the goal of the stimulation is to connect these wells and be able to circulate very efficiently between the injection and production well. So, whoops, sorry. So from an overview, this is, I'll show more detail on the pad itself. This is the injection schedule that was followed. So started out at 2.5 barrels a minute for a day, shut to generate some initial more transient kind of analysis in the reservoir, shut down for 8 hours, and then sequentially increased the rate up to 10 barrels a minute, where that was the rate that remained, that stayed for the next 28 days of pumping. So the simple setup was to use 125,000 barrel pit here, which was basically well water from one of the offset pads on a water well that Forge has. We added chemical additives to treat for corrosion and scale inhibition. We used frac pumps in this case to pump the 30-day treatment. and pumped into well 16A, flowed out of well 16B, had a geothermal separator, atmospheric separator that flowed back into a sump. And then we transferred this water back to the 125,000 barrel pit and just used that for the circulation the entire 30 days. So the intent is to know what you're injecting into 16A, goes down up through the fracture system that connects, to understand what comes out of 16B before it goes into the separator. And then when it goes into the flash separator, atmospheric, obviously flashes steam and then drops out the remaining water that flows out to the sump. So instrumentation wise, put all flow meters, pressure transducers, temperature probes, sampling ports, significant effort made to collect all the necessary data to understand how the system was behaving throughout, and to be able to take a lot of samples for different types of analysis, and primarily, obviously for the tracer analysis, but for a lot of other understandings on water chemistry, geochemistry, and things like that. This is how it was actually, set up, just to see the actual setup, the pumps, the 16A injection well, the 16B production well, the separator, the sump, and then all of the associated equipment back behind here to transfer back to the 125,000 barrel pit and continue the circulation. So a very overview summary. I didn't mention, I took out for time's sake, there was a 9-hour circulation test that was done immediately after fracturing. However, the result was that the efficiency was getting better over time, and the main reason is because during the frac treatments we injected about 130,000 barrels of fluid into the reservoir to create the fracture system. But to drill out the plugs using the workover rigs, we had to flow back about 70,000 barrels of that fluid in order to have pressure conditions and safety conditions met at surface so that we could safely drill out the frac plugs with the workover rig. So most of this 9 hours, well, all of the 9-hour circulation test was simply kind of refilling, recharging the system because we had flowed back so much of the water out of it. So the long-term circulation, 10 barrels a minute between the wells for almost 30 days. Actually, the efficiency was approaching and exceeded about 90%. So 90% of what we were injecting into 16A was being produced out of 16B. Steam fraction was about 19%, and the produced fluid temperature for the last few days was constant at 370 degrees Fahrenheit and above. So we ran production logs also during the long-term circulation test. So the interesting thing here, and again, there's a lot of data and reports on this, but when you look at the contribution of injected fluid into the different frac stages, you can see that stage 10, stage 9, stage 8, all very high contribution. And stage 7 and stage 6 that didn't get any proppant pumped into them actually showed no injectivity. Stage 5 showed a small amount of injectivity, and stages, so the log only got down to just below stage 5. So stages 4 and then everything for stage 3R is lumped together as 26%. So one thing I didn't get to do on here was, this looks really low, of course, but this is a single cluster. These are 8 clusters, and 10 is a single cluster. But when you look at the data, you'll think there's a lot of evidence here that these two are connected to the same fairway. So just maybe an artifact, but maybe also has something to do with the fact that this was the test case for the ultra lightweight proppant. So just breaking it down by percentage relative to all the stages in the A well, or just relative in stage 9 only, you can see this is the heel, this is the toe. So, every cluster in stage 9, all 8 took injected fluid. You could say this might be a little bit heel dominated, but you know, I don't know if that's really a valid conclusion or you know, just what the data is showing at this particular time. Stage 8 being the crosslink stage, same plot. Now it shows most of the injection into the stages near the toe part of that stage. The lower clusters in that stage, more towards the toe, are the ones taking the majority of the fluid. But again, I don't know if that's significant or just kind of an artifact of the time that this measurement was made. We also tried to log in the production well while it was flowing. Stage 5, stage 4, we only got the log down in between stages 3 and 4. So the stage contribution only shows up as stage 5, stage 4, and stage 3 and below. But the interesting thing is that stage 5 is producing 25% of the fluid. Stage 5 wasn't fracture stimulated. This was just perforated. So it's definitely an interesting result. And then if you look at stage 5, just the perforated interval only, yeah, most of the contribution comes through 2 of the 4 clusters. One of the clusters produces is just a trace of fluid coming through there. And then if you look at stage 4, which was fracture stimulated, you get a bit more evenness of fluid entering through the different clusters. So the good news is all of the data and reports and everything are available to anyone who wants to download. Go to the Geothermal Data Repository, the GDR, or the University of Utah Forge Wiki site and download any and all of the data that we've looked at and a whole lot more. So with that, I'm going to stop and let it go to questions.
And thank you, Kevin. Great project and great overview. And we do have a few questions. So Claudio is interested is whether or not any defits were run on this particular frac campaign.
Well, no, not in this particular work here. There were some initial injection tests done on 16A when it was first completed, and I think John, you did those were in 2019, 2020, and there are data and papers and everything available on all of that.
So there was a defit run in the open hole section. And in 2022, there were a couple of shut-ins before proppant and after proppant that might be useful to look at. So John's question is, any thoughts on the amount of leak off seen at the end of each stage? Seems like granite would not leak off, but pressure does come down fairly quickly after pumping stops.
Well, after pumping stops, the fracture generation doesn't stop. So there's a lot of microseismic activity after shutdown. Because there's no real leak off in the granite, the fractures actually keep propagating, and we keep generating microseismic data for quite a while after the actual treatment is shut down. So that's responsible for a vast majority of the pressure decline.
And
John, this is Ali Danishi. Let me just make a comment here, which is important. The other reason the pressure is declining the way you see it is because pressure inside the fracture is not constant. So as the pressure equalizes within the fracture with time, that causes the wellbore pressure to drop.
Indeed. Yeah.
There's a lot of things dynamically happening in the fracture system for quite a time after shutdown.
And Raj mentions that the indications are that we do need proppant.
I mean, just looking at that high level overview, I think that's a good conclusion.
And Ed's asking about gamma ray. You mentioned that spectral was only run on 16A, but I think every other well at the Forge project has had a comprehensive set of logs, usually quad combo plus imaging.
Yeah, and I think, one of the action items after all of that obviously going on now is taking a much more fine detailed look at um, logging information in the past to see if anything, like what we see in that particular case in 16A is noticeable in other logging data sets.
And Raj has another question, and his second question is whether or not the fiber can fill in some of the pressure profile on 16B.
Yeah, so we don't have a full, um, I guess, curated set of data from the pressure gauge actually in 16B yet, but that's definitely going to be another piece of the puzzle to help understand everything that was going on.
But correct me if I'm wrong. I think Nubrex is also looking at trying to match the PLT with strain data
Yeah.
and characterize the lower production.
Yeah, so that's true. And other, the tracer data will also provide a lot of insight into, what's coming out as a function of time, and hopefully, again, um, be correlatable to PLT data or representative of PLT data. The one thing I didn't get to mention was, we also ran the EV clear vision downhole camera and ultrasonic in the 16A well because it was cooled down enough to be able to run that tool. And the analysis is still being finalized. What I can say is that I know that they have commented they've seen that all of the perforation clusters look like they have some degree of erosion, and some more than others, but that more relates to the phasing of the perforations, and things are looking to line up pretty well there. So I think that'll also be very, very helpful in the more detailed analysis as time goes on.
So the next question is a good one, Kevin. Was 10 barrels per minute the maximum you could reach on the long-term circulation test?
Yes. I mean, so the idea on the circulation test was to make sure that you stayed below generating additional fractures to just hopefully stay within circulating in the system that was created. We were very close to that maximum pressure early on, but as the circulation continued, the pressure was decreasing with time. I'm sure partly because of the cooling effect at the entry to the fractures, creating some dilation in the fracture system near the 16A wellbore. But yeah, we didn't have room to go really much higher.
So do you want to comment how that might compare with a commercial situation where the perforated length, the number of clusters would be much, much larger?
Yeah, so I mean, it seems, like a low rate, commercial rate, but the number of clusters that we're injecting through are, I think, 23 number of clusters. So, at 10 barrels a minute, and if you look at other work that's been done, published by Fervo, I think, their rates are much higher, but the number of clusters are a magnitude higher than what we're injecting through here at Forge. So I think it's really kind of, kilograms per second per cluster, pretty much all kind of on par with each other, I believe.
So the next question is from Luke, and he'd like you to comment on why the wellhead pressure was downgraded to 8,000 psi?
So the 16A wellhead, I'm going by what I've learned when I started work helping with forge, but it's a screw-on wellhead. It's not a welded wellhead, and it's been on there a long time. And there are some issues with the um, completion quality in the upper part of the well, and so 80% of the maximum working pressure rating was decided as the maximum pressure we would go to while pumping.
Let's see, what's next? Awais, he's curious about the variations observed for the different fluids. What were your your deductions or conclusions?
Well, so when you look at the amount of cool down that you have in 16A during the course of the pump down and plug operation, I mean, we're very cool down at the perforations whenever we're pumping each of the stages. So, we have with the crosslink system a lot of viscosity at the perfs, whereas with the slick water system, we, have water viscosity at the perfs. The idea is, I think mainly with the viscosity is to try and make sure we have enough connected width between the clusters and the fractures that are created in the formation in order to get proppant through there without restriction and bridging. And maybe the viscosity could also have an impact on, the initiation and somewhat, how the fractures start to propagate, which, could uh, be important in terms of the connection between one well and the other. But the conclusions are still to be determined. I think for sure it helped with the entry of proppant into the fractures because of the deviated wellbore and maybe a bit tortuous connection between the wellbore and the fractures, which also you can look at the pressure data and see that when we shut down, there's a significant amount of pressure drop, way more than the little bit of friction pressure that we have at these rates in 7-inch casing.
And John is wondering, we lost 10% of the mass that was injected. Where do you visualize that went?
Well, I don't know if I'm good at answering that question. I mean, so there were some issues with monitoring on, what we were actually getting out of the 16B well. And that had to do with some failures of some sensors and some of them that were uh, having poor response to the temperature that we had, even though they were rated for temperature. Um, there could still be some filling up of some voids in the fracture system downhole. I think when you look at the fact that the production well and injection well, how they're positioned, with the production well being vertically straight above the injection well, I mean, everything down below could be re-energizing or opening up additional fractures that were open initially but had closed um, during the plug drill outs and things like that. If we would have circulated longer, it's possible that we could have gotten pretty close to volume in, volume out.
So just in the interest of time, Luke has put down 4 of his conclusions. I think maybe the one to comment on is whether or not the producer needs to be fracked.
Well, so I guess the evidence that we have right now is the fact that we are circulating to stage 5 in the producer well, which wasn't fracked. I don't think it's enough consensus, to say that it wouldn't be beneficial to frack to enhance the connection, but it does seem like the connection, even without fracturing it, on the B well is still there.
The only, and I don't want to get into an argument here with the
No.
speaker, but the only factor that's contrary to that is that in 2022, immediately after 16B was drilled, when it was not fracked, a circulation test was done through the 3 fractures that were created at the toe of 16A, and there was no communication. And I think that's pretty telling that without stimulating those, there was no communication whatsoever. Nabil, let's see. Thanks, good stuff. Higher prop concentration. So I don't know whether you can see this, Kevin. Nabil's question is was there any variation in the proppant concentration as a function of the fluids? And also, what did the ultra lightweight proppant state show on microseismic data?
Yeah, I don't know the answer to the last question yet. I know, that there's probably going to be a lot of overlap now because stage 10 seemed to basically frack in the same corridor as stage 9 did. So I don't know if we're going to be able to really discern a lot of difference between the fracture geometry behavior. But what was the first part of the question? Sorry.
Just whether there was a different proppant schedule for crosslink versus slick water.
No. The proppant schedule is the same for both.
And just following up on this, the last and final question is what percentage pad was pumped, and was that different for any of the different stages or fluid types?
No, it was the same, and the percentage, I think I'm gonna probably 15%. I don't know that really was designed as pad and proppant. Basically, the pad was to make sure we generated enough width at the wellbore before we started proppant. It obviously wasn't to try and keep from losing all that fluid due to leak off, because there really wasn't any leak off.
I believe that's the last question. So Kevin, I'd really like to thank you, and sort of as a testimony to the quality of the presentation, you've still got 2/3 of your audience listening in, and even though it's after 10 o'clock Central Time. So thank you, fantastic presentation, and thanks to everyone who listened and participated.